Okay, good evening all of you. Today we are going to do the chapter Dual Nature of Matter and Radiation. So, in this chapter, nature of in this chapter Dual Nature of Matter and Radiation, we are basically going to discuss two things. One is that we are aware that light is an electromagnetic wave and light is made up of photons, so we are aware of that. Uh, but can photons also interact with particles? So photons are supposed to have wave-like nature, but is it possible that photons can interact with particles? So that is the first thing. The second thing is that can we also have the opposite situation? That means can we have some particles which have wave-like nature? So that is what this chapter is all about. So dual nature of matter and radiation. So photons are the components of waves. So do they have capacity to interact with matter? And secondly, um so Krishika, but I won't be able to clear a single or I have a screen which will only. Actually, I have to take her class to come early. Oh, okay. So that is what this is about. So we'll be discussing this now.
Six.
L square. 6 L.
J collector.
Okay, so basically the first half of this chapter we'll be discussing that can photons interact with particles. Like photons are the constituents of waves. But in the first half of this chapter we'll discuss that can photons interact with particles. So suppose there is a highly evacuated glass tube. Okay, this is a highly evacuated glass tube. Like either there is a vacuum or there is a gas at low pressure. So inside this glass tube, either you will have a perfect vacuum or you will have gas at very low pressure. So there are two terminals inside this glass tube. The one terminal which is attached to the negative of the cell, that is called the cathode. And the terminal which is attached to the positive of the cell, that is called the anode. So there are two terminals. The terminal attached to the negative of the cell, that is called cathode, and the terminal attached to the positive of the cell, that is called anode. Now in this experimental setup, so this is called so this is actually the photoelectric effect experimental setup. So in this setup, what is happening is that there will be light falling on the cathode. Okay, light of a certain pre-decided frequency. Like you all know that the primary properties of light are velocity, frequency, and wavelength. Velocity of light is near about 3 into 10 to the power 8 meter per second, and the frequency and wavelength are alterable. So we have a certain pre-decided frequency, and that light is falling on the cathode. So light of a certain pre-decided frequency is falling on the cathode. Now what happens is that there is a circuit over here, as you can see. So there is an ammeter. There is an ammeter over here. Okay, there is an ammeter. There is a circuit. There is a positive. There is a negative. There is an ammeter. So when light of a certain frequency falls on the cathode, then a stream of electrons comes out of the cathode, goes up to the anode, and the circuit is completed and the ammeter shows a reading. And that is what this experimental setup is all about. So a light of a certain pre-decided frequency falls on the cathode, a stream of electrons comes out of the cathode, goes towards the anode, and the circuit is completed and the ammeter shows a reading. So this setup is called photoelectric effect experimental setup. Now the thing is that a few observations were made regarding this experimental setup. A few observations were made. First of all, this light has got photons, and if the light has got larger number of photons, then the intensity will be high. If the light has got lesser number of photons, the intensity will be less. So the first thing is the intensity of the light. So which we in common parlance we call it brightness. So the intensity of the light is related to the brightness. So if you have bright light, it will have many photons. If you have dim light, it will have lesser number of photons. So the intensity of the light is plotted on the x-axis, okay, and the current that is flowing in the circuit is plotted on the y-axis. So the intensity of light is x-axis, and photocurrent, that is the current that is flowing through this circuit, that is plotted on the y-axis. So it was found that the photocurrent and intensity graph is a straight line passing through the origin. So the graph of photocurrent versus intensity is a straight line passing through the origin. That means the photocurrent and intensity are proportional. If you increase the intensity, you will get more photocurrent. If you decrease the intensity, you will get less photocurrent. So the graph of photocurrent and intensity is a straight line. Then we come to the next graph, that is potential of the anode versus photocurrent. So when the potential of the anode was increased, right, then that means the anode is going to pull the electrons much more, because you are increasing the potential of the anode. That is, anode will pull the electrons much more. So if you increase the potential of the anode will pull the electrons much more, and the current should rise. But one interesting observation was made, that the current does rise, but it does not rise indefinitely. After a while, the current becomes horizontal. That means it becomes constant. So when the current becomes constant, that is called saturation current. So the thing is that saturation current means that now the current has become constant. So when you increase the positive potential of the anode, then the anode starts pulling the electrons towards itself, but those electrons do not get a very smooth passage to the anode. They keep colliding with each other while they are going towards the anode. But if you keep the anode potential sufficiently positive, then the electrons will all get comfortably pulled to the anode, and when that happens, you will get a proper reading in the circuit, and that is called saturation current. So you will observe that there are three saturation currents, I3, I2 and I1, right? There are three saturation currents. There are three saturation currents, that is depending on the intensity, I3, I2 and I1. So if you increase the intensity, the current will increase. So I3 is the highest intensity, so that is why the current is maximum. So for intensity I3, the current is maximum. I2 is second, so the current is second, and I1 is the least, so the current is the least. So I3 greater than I2 greater than I1 is what is the comparison of intensity of these three graphs. So because I3 is the most and I1 is the least, that is why the saturation current is most for I3 and least for I1. Acha, another thing is that suppose if you do a turnaround, that means suppose if you make the anode negative and cathode positive, suppose if you turn things around, like now you make the anode negative and cathode positive. So if you make the anode negative and cathode positive, then realistically what should be happening, that there should not be any photocurrent at all, right? Because now anode you have made it negative, and what is coming out of the cathode? Electrons. So if you make the anode negative, you should not get any photoelectric effect at all. But that happens slowly, it doesn't happen all of a sudden. So you can see the graph is going down, and finally when the potential becomes minus V0, that time when the potential becomes minus V0, that time the current becomes 0, right? So this is the thing, that for higher value of intensity, I3 greater than I2 greater than I1, you will get a higher saturation current, and the potential of the anode at which photoelectric effect will completely stop is minus V0. So at this potential, the photoelectric effect will totally stop. So when the anode potential with respect to cathode becomes minus V0, the photoelectric effect will fully stop. That means the anode will no longer be able to pull the electrons towards itself. So this is the graph number 2. So from graph number 1 and graph number 2, from these two graphs, what did we learn? We learned two things. One is that the photocurrent is proportional to intensity. If the intensity of the photon beam is more, photocurrent will be more. And the other is that the photocurrent, the stopping potential does not depend on intensity. So the photocurrent depends on intensity, but the stopping potential does not depend on intensity. This we can understand from these two graphs, because when intensity is very high, medium, low, all the time the stopping potential is the same. So from these two graphs, the summary is that photocurrent is proportional to intensity, so it depends on intensity, but stopping potential minus V0 does not depend on intensity at all. So from these two graphs we can conclude that. Now there is a third graph, this one. Now in this graph what we have done, we have taken three different photon beams. I explained to you that the photon beam will have a frequency which is pre-decided. So you have three photon beams. Frequencies are nu1, nu2 and nu3. There are three photon beams. Frequencies are nu1, nu2 and nu3. And these three photon beams, when they are falling on the cathode, then what will happen is that you will have photoelectric effect for each of these photon beams, but that photoelectric effect will give you the same saturation current. So the frequency of the light, if it changes, then it will only it will not affect the saturation current. That means frequency does not depend on does not affect saturation current. On the other hand, if the frequency is high, then the stopping potential will be high. If the frequency is low, the stopping potential will be low. So this is the comparison. Okay, this is the comparison of frequency nu3, nu2 and nu1. So if the frequency is high, the stopping potential will be high. If the frequency is low, stopping potential will be low. So that means the frequency does not depend on the stopping potential. Rather, the stopping potential does not depend on the frequency. The stopping potential depends on the frequency. Saturation current does not depend on the frequency. So that is the conclusion from graph number 3. Okay. Now, and finally, there is another graph. Okay, and finally there is one more graph, this one. Now in this graph, the y-axis you have got stopping potential, and the x-axis you have got frequency. The y-axis is stopping potential, x-axis is frequency. Now in this graph, what is happening is that you have two different metals A and B. You have two different metals A and B. So there are two metals A and B, okay? And the graph of stopping potential versus frequency for these two metals A and B will look exactly like this. So this one will be the x-intercept. This is called mu naught for A, and this x-intercept, this one is called mu naught for B. So mu naught is called the threshold frequency. Okay, mu naught is called the threshold frequency. Threshold frequency literally means the minimum frequency for photoelectric effect to take place. So when you draw the graph of stopping potential versus mu naught for two different metals A and B, the graph will be a straight line and the x-intercept will be the threshold frequency. Okay, so from these four graphs, whatever we have observed from these four graphs, so now let us look for the
volume of the wall. ভলিউম অফ দ্য ওয়ালটা শুধু ভাগ করা অঙ্কটা আমি করে নিচ্ছি।
Okay, so now we have studied the four different types of graphs. Now what we will do is we will now discuss first of all why this entire thing is happening. Why is this photoelectric effect happening? What is the mechanism of photoelectric effect? And that will actually help us to understand these four graphs better. Okay, and then also some properties of photons. So that's what we are going to discuss. So first of all, let us discuss that why does photoelectric effect happen. Let's begin with that. So light is falling on the cathode. So first thing is that light is falling on the cathode. So when light falls on the cathode, what happens? The cathode is a metal. Okay, the cathode is a metal, and the cathode has got free electrons just like any metal. So when light falls on the cathode, then the photons of light, they penetrate inside the cathode and they collide with the free electrons of the cathode. So the photons of the light, they penetrate into the cathode and collide with the free electrons. When the photons collide with the free electrons, so that is where the dual nature concept is coming, that photons are essentially the constituents of waves. So photons can interact with particles. So that is what is coming out of this experiment, that photons are the constituents of waves, but they can interact with particles. So photon is entering the cathode and interacting with the electrons inside the cathode. And instead the photon itself will be converted into another photon of lower energy. That is one possibility. The other possibility is that the photon will completely self-destroy and give its entire energy to electron. So there are two possibilities. So once again, either the photon will give a part of its energy to electron and it will change into a photon of lesser energy, or it will self-destroy and give all its energy to the electron. So these are the two possibilities. So
ওয়ালটা কিউবয়েড হবে তাই না?
So what we will do is, we will say that suppose the photon it gives all its energy to the electron. Let us say the photon will give all its energy to the electron. That means it will self-destruct and it will give its entire energy to the electron. So when the photon gives the entire energy to the electron will get this much energy, h into frequency, and from this you have to subtract work function of the metal. From this you have to subtract work function of the metal. What is work function? Work function of any metal is the minimum energy that you must give to an electron inside the metal to just come out of the surface of the metal. So for any metal, when you say work function, then it is a minimum energy that you need to give an electron so that it just comes to the surface. So an electron, after receiving energy from the photon, will just come to the surface. After coming to the surface, it will accelerate towards the anode. So the energy received from the light is h into frequency. So that minus the work function will become the energy of the electron. And with that energy, the electron will accelerate towards the anode. So the situation which we are considering, we will say that this is the situation where the electron is getting maximum possible energy because the photon is completely giving its energy to the electron. So I am calling it as Ke max. If you want, you can also write half mv square max. Okay, you can also write half mv square max. So half mv square max is the kinetic energy of the electron. With this kinetic energy, the electron is going towards the anode, and the photon energy minus the work function is equal to half mv square max. So this explains to us what is happening up to the time the electron comes out of the cathode. Now the electron has come out of the cathode and the electron will accelerate and go to the anode. Once it goes to the anode, the circuit will be completed. Now let's go to the next part of the discussion, that if I increase the intensity, then I am getting more photons. More intensity means more photons. Those photons are going to collide with the cathode, so I'll have more collisions with electrons, so I'll have more electrons coming out. More electrons coming out means more current. So if I increase the intensity, the current will also increase. So this justifies this graph, current versus intensity. Okay. Next thing is that if I decide to make the anode negative, suppose I decide that I will make the anode negative. So when I make the anode negative, then what will happen? The electrons, instead of being accelerated towards the anode, they will be resisted by the anode. And if I make the anode sufficiently negative, minus V0, then even this most energetic electron will find it difficult to reach the anode. So that means we can say that E into V0, that means you all know that the work done in accelerating an electron or retarding an electron is basically charge of electron into the voltage through which it is accelerated or retarded. So charge of electron into V0 is the is causing the retardation or acceleration of the electron. So E into V0 is h into frequency minus work function. So that means EV0 is half mv square max is h into frequency minus work function. So this is the full equation of photoelectric effect, and that explains that when you change the intensity, V0 is not affected, because you can see V0 depends on frequency, V0 doesn't depend on intensity. So that now confirms to us that why stopping potential is not related to the intensity, because stopping potential depends on frequency, it has no relation with intensity. Now coming to the third graph, here what is happening, I am increasing the frequency of the incident beam, so nu3, nu2, nu1. So when the frequency is high, right, the stopping potential is high. You can see that they have a direct relation. If you increase frequency, stopping potential will increase. So when the frequency is nu3, stopping potential is V03. When the frequency is nu2, stopping potential is V02. When it is nu1, stopping potential is V01. So the stopping potential is V03, V02, V01 accordingly as the frequency is nu3, nu2, nu1. Right? These are the values. So this is the formula. EV0 is half mv square max is h into nu minus the work function. So this is the formula which completely explains the photoelectric effect. Okay, now earlier I had explained to you about this threshold frequency. So threshold frequency actually is given by nu naught, such that h into nu naught is work function. So h into nu naught and work function will cancel each other. So EV0 will become 0. That means what? That this is the minimum frequency of the incident beam for which photoelectric effect will be successful. If the frequency is below nu naught, you will not get any photoelectric effect at all. So threshold frequency is the minimum frequency for successful photoelectric effect to happen. So if you want, you can make one alteration, that you can write h into nu minus h into nu naught. You can write this also, right? So instead of writing h nu minus work function, you can write h nu minus h nu naught. You can do that also. So this is the details of photoelectric effect. Now coming to the third graph. In the third graph, the frequency nu3 is the highest and nu1 is the least. And you can see here that for all three frequencies, the saturation current is the same. So now we have understood, this is the thing, we can write it like this. So this intensity and stopping potential. So the intensity, this is photocurrent, so it depends on intensity but doesn't depend on frequency. Stopping potential depends on frequency but doesn't depend on intensity. So this is the thing. So here you can see that when the frequency is nu3, stopping potential is V03, when frequency is nu1, stopping potential is V01, but the saturation current is the same for all. Now we come to the next graph, that is stopping potential versus frequency, this graph. So V0 is h by E into frequency minus work function by E. So V0 is h by E into frequency minus work function by E. Now this is the slope of the graph. So if you draw the graph of stopping potential versus frequency, so this is stopping potential, this frequency. If you draw the graph of stopping potential versus frequency, then h by E will be the slope of the graph. So you can see that for different metals, the slope of the graph will be the same. Whether it is metal A or metal B, all the lines are parallel because the slope is h by E, which is the same for all. And the y-intercept is work function by E. So for different metals, you know, the work functions will be different. So for metal A and metal B, the y-intercept will be different because they will have different work functions. So this straight line is represented by these two parallel lines, and that explains why you will have parallel lines because the slope is h by E for all of them, but the y-intercept will be different because work function is different for all of them.
So number 9 to volume of the liter very but confusion of the calculation. Number it can be 4500.
So, what are the important things to note that we have already discussed? Photocurrent depends on intensity but not frequency. Stopping potential depends on frequency but not intensity. And the last graph, the slopes are equal because they are all h by E, and the y-intercepts are different because they are all w by E. Another thing is that in photoelectric effect there is no time lag. That means the moment the photons hit the cathode, from that time till the time the current is first perceived, the time lag is so the time lag is 10 to the power minus 9 seconds or less. So the time lag is 10 to the power minus 9 seconds or less. So this 10 to the power minus 9 seconds is such a small quantity that it is ignorable. So that means there is hardly any time lag. So photoelectric effect, we can say that it happens almost instantly. Okay, there is no time.
20 by 100, 20 by 100 হলো না?
No, আমি সব সেন্টিমিটারে করে দিলাম because ব্রিক্সটা সেন্টিমিটারে ছিল।
আচ্ছা।
So based on this experiment of photoelectric effect, what are the conclusions? So what are the properties of photons? So number one, they behave as particles in their interaction with electrons. Okay, when they interact with electrons, that time they behave like particles. So that is property number one. The energy of a photon beam is h into frequency, momentum is h into frequency by speed of light. So energy doesn't depend on intensity. Number four, they are electrically neutral. Okay, so the total energy and total momentum in photon and electron interaction, the total energy and total momentum is conserved, but the number of photons is not conserved. Okay, so this is important. You can have photons self-destroying and giving energy to electron. So photon behaves like particles in interaction with electron. The energy is h into frequency, momentum is h into frequency by speed of light. The energy of a photon doesn't depend on intensity. They are electrically neutral. The total energy and total momentum is conserved whenever photons interact with matter, but the number of photons is not conserved. Okay, then next we have wave nature of matter. So according to the scientist de Broglie, he said that just like photons can interact with particles, electrons can also show wave-like nature, and the wavelength associated with an electron is lambda equal to h by mv. Okay, so the wave nature of matter, the wavelength associated with an electron is given by lambda equal to h by mv.
So, number 10 होगा. Number 10.
Kinetic potential of V is K equal to E into V. Okay, this is the wait 1.5%. Ready, come on. So the kinetic energy of an electron accelerated through V, that is charge of electron E into the voltage V, and suppose that is equal to half mv square. Now the momentum of an electron is root over of 2 into mass into kinetic energy. So kinetic energy you write EV. So root over 2 into mass into EV. So this is the momentum of an electron. Now wavelength is h by mv, that is h by root over 2 into m into EV. So in this formula, if you put the value of h, mass of electron, charge of electron, and 2 everything, if you put, you will get 1.227 by root v. This will be the wavelength, and it will be in nanometer. So this will be the wavelength in nanometer. So if you put v is 120 volt, then lambda will come 0.112 nanometer. So this is the practical application of the de Broglie wavelength. Okay, now this is a low voltage battery. It is attached to the cathode. We call it a filament. This is a high voltage battery. The high voltage battery will apply a potential difference between the cathode and the anode. Okay, the high voltage battery will apply a potential difference between the cathode and the anode, and this filament is what I am calling the anode. So this is a low voltage battery. So from the filament a stream of electrons are coming out, okay, because the low voltage battery will energize the filament, and that is called thermionic emission. A stream of electrons will come out. Now this stream of electrons will pass through the anode and it will hit a nickel target, and nickel crystal has got very fine spacing, and there will be diffraction, and diffracted beam is collected by a movable collector which takes it to a galvanometer. So this was the experiment conducted by Davison and Garner. The purpose of this experiment was to prove the wave nature of electrons. So in this experiment, this voltage was varied from 44 to 68 volt, and the diffracted beam, okay, the diffracted beam was taken by a movable collector to a galvanometer. So if the galvanometer shows a strong deflection, that means the intensity of the diffracted beam is high. If the galvanometer shows a gentle deflection, that means the intensity of the diffracted beam is less. So it was found that when the voltage of this was 54 volt, okay, when this voltage was 54 volt, then we got maximum intensity for angle equal to 50 degree. So at 54 volt, the maximum intensity of the diffracted beam came when theta is 50 degree. So now there is one law which is actually not in the syllabus, so I am skipping the law. There is a law called Bragg's law. According to this law, the electron waves, their wavelength works out to 0.165 nanometer. So this is the wavelength of electron waves. So that technique is called Bragg's law. And in the formula 1.227 divided by root over V, if you put 54, it is coming to 0.167 nanometer. So by Bragg's law, it is 0.165, and by the formula 1.227 by root V, it is coming to 0.167. So this is a confirmation that electrons can show wave-like nature. So that was the aim of this experiment. So you could say that this experiment completes the chapter which began with photoelectric effect experiment. So photoelectric effect experiment confirms the particle nature of photons, and this experiment confirms the wave nature of electrons. So this completes the whole chapter, dual nature of matter and radiation. So on that note, I'll conclude this particular session. I'll end this session now. Thank you. Bye all of you.